Thank you very much for the organizers to giving me the opportunity to speak here. And I was told that I should make this an accessible talk, which makes sense. So the title is a bit daunting, but I will. So these coefficients that are listed there, they'll come on one of the later slides. So it will be. I will say a lot of things. I will start saying a lot of things that have been said before, maybe in a bit a different way. Also, so we have not talked to each other, but we will, so the three speakers of today, but I will repeat a lot of things that have been said today. So it will be slow, and if you have any questions, just feel free to interrupt me and ask anything, right? So this is the first one. I hope it's not too tiny, because it's projecting not to the whole screen, but I will also tell you what's written there. So, okay, we start with a permanent. This is our polynomial that we want to have a look at. As m, the symmetric group on m letters, right? You just multiply those. We all know this nice function. And is v and p complete as a polynomial, sharp p complete as a function. And Greta showed us how to write the permanent as a determinant of a matrix of size 2 to the m minus 1. I guess that was actually discussed in the bootcamp. So this is one example, right? The permanent, 3x3 permanent, is the determinant of this matrix, right? And you could calculate that and see that this is true. And the proof that he gives is an explicit construction of an algebraic branching program of that size. And from there, so you get exactly this matrix, and the matrix has only zeros and ones and variables, right? That's what you get out of his construction. And with Hüttenhain, in this specific constant-free model, with Hüttenhain, we ask ourselves, is this optimal? So can you get the 3x3 permanent maybe as a smaller matrix? Just having zeros and ones and variables, and we calculate it. It's a computer calculation, so it is not possible. You cannot get a 6x6 matrix. And then a few months later, Alper, Bogart, and Velasco proved that you cannot even get a smaller matrix for when you allow affine linear forms in these entries in the matrix cells. So if you allow not just the variables being there in these cells, but a linear combination and also maybe some constants also in each cell, right? Even then you cannot get a smaller matrix. So this is optimal. So of course Valiant now then showed you can write every polynomial. So the polynomials will be h. So this will actually be important. So these polynomials, like the permanent on these slides, they will be h. For like a hard polynomial, say something you want to know the hardness of, right? So that would be h. And this can be written, they can be written as a determinant, and dc should be the smallest size that's possible. So in our case, dc of the 3x3 permanent is 7, right? Okay, that we know. The best known lower bound is the Mignon-Resser bound from 2004. It's m squared over 2. And so the first reference I found for this problem is a 1913 reference by Polya, where Polya studied this in a toy case. It's actually a task for interested readers to study if they could change signs in a matrix if they calculate the determinant, that the result would be the permanent, and that works for the 2x2 case, but it doesn't work for any larger case. That was the first occurrence that I found where this is discussed. All right, but now, so this is quite combinatorial, this construction of this algebraic branching program. So we want to make the transition to geometry, and this transition to geometry is precisely by the approximations that we heard so much about today, right? It's precisely this. So let's just assume we are working over the finite field of over the field of complex numbers. So I don't want to have any trouble. So it's complex numbers for my talk the whole time. And this is just a cooked up example. It's nothing spectacular here. This is my polynomial h. You just you have this polynomial here and a matrix, and it has an index epsilon. So this matrix looks like this. Has some epsilon inverses here, but its determinant does not have any epsilon inverses. Its determinant is precisely h plus some term that vanishes if you let epsilon go to 0, right? But note here that, I mean, here in this example, you can see it really nicely. The single matrix entries, if you let epsilon go to 0, those entries diverge, right? So the matrix itself does not converge, but its determinant does, right? Because of cancellations, right? So this is very nice here, right? So in other words, this H here can be approximated arbitrarily closely by determinants here in this case of size 4. Right? So DC bar should be the size of the smallest matrix sequence where the determinants approximate H. Right? So it's exactly the same DC bar. I do the bar under the DC instead of over the DC, but I mean that's just for taste. Right? It's the same DC bar. Well, in this example, DC bar is less or equal to 4, but it might be that DC is bigger than 4. Or also, we've seen examples now. There was one example on the board where the DC bar was 3 and DC was at least 5. So we know that there might just be gaps, right? And you see, in this case, it's also not clear that you find a 4x4 matrix that gives you this polynomial as a determinant, right? So this lower bound, this m squared over 2 lower bound, this also works for DC bar of the permanent. It's also m squared over 2, but it's a different paper. It's a later paper by Landsberg, Multiplicities, and Resser. And we encounter the first open question. That is DC bar of the 3x3 permanent. That is not known, so it's 5, 6, or 7. Right? So this is, and mathematicians are well aware of this question, and they think it's very interesting, and in particular geometers. But yeah, this is still open. So if you could figure that out, that would be great. So there is the recent result by Alpa, Bogart, Velasco. It only gives you the bound for the DC, not for the DC bar. First open question. Yep. Yes.
So the Mignon-Resser lower bound is also a rank of the Hessian, right? So why does that not?
That does not give a DC bar bound. No. That the Mignon-Resser bound does not give you a DC bar bound. But why does it not? It's a good question. I would have to.
No, I mean that Landsberg-Resser basically is algebraization of that the same condition.
Okay. I see. Yeah. So you say they are so. I see. So okay. We can try to figure that out. Okay. So also this question has been asked before. So maybe let me just restate this question because it was also the question that I was thinking of. So clearly there's the DC bar of the permanent is less or equal to the DC bar DC of the permanent. Yes, but how large is the gap? So in principle it could be really, really, really bad, right? As far as we know, it could be that the DC of the permanent could grow superpolynomially, and that's Valiant's conjecture. While at the same time, it could be that the DC bar of the permanent could just grow polynomially, right? That's the worst case that could possibly happen, but we don't know this. So there's Montmollet and Sony's conjecture was also on the board, right? DC bar should grow superpolynomially, right? So I'm not saying that I believe this. I mean, not in any way do I believe this, but we just don't know what's going on, right? So could we at least now prove the following implication? That would now be very nice. So, and this is also like, I think this has been mentioned by both the other speakers today, right? It's, could we at least prove that these two conjectures are the same, right? So if DC bar is polynomially bounded, then the DC should also be polynomially bounded, right? This is precisely a question about qualities of approximation and what happens if you go to the boundary, right? It is precisely such a question. Some remarks. So we have not seen today the setting of the bilinear complexity, where you can actually show that the transition to these approximations is harmless. So if you do this for the matrix multiplication tensor, and you look at rank, and on the other hand border rank, which is precisely the same transition, then you actually can prove that these two grow with the same order of magnitude omega. So and now the question is, can one somehow lift this to the permanent? So an integral part of this proof for the matrix multiplication tensor is some self-reducibility property of the matrix multiplication tensor. So in particular, the following: if you have a matrix multiplication tensor and you take its tensor power with itself, this will result in a bigger matrix multiplication tensor. That's a key part of that proof. And the permanent has some properties that can remind you of that, but they are somehow not strong enough that it's very easy to translate this proof, right? I mean, you have also a permanent consists of a sum of smaller permanents and things like that. I mean, but it's not. I mean, it's not so easy to lift this proof to the permanent question here. And yeah, so most lower bound techniques. Oh, that's a typo here. But most lower bound techniques. I mean, this has also been in the previous talk, right? They cannot actually distinguish between DC and DC bar. So if you prove a lower bound on DC, most techniques already also give you a lower bound on DC bar, right? So there are good reasons now to study DC bar, but I mean, there are also very, very good reasons to ask ourselves, should we, I mean, how reasonable is it? I mean, can we actually prove that it's okay to study DC bar, right? That is I think that's key. We should understand that. Okay. So, yeah, so this is a very bold title of this slide. So if we study DC bar, if we accept that we want to study DC bar, then we can actually prove a lot of things about how lower bounds, what I say must look like, but I mean I can be very precise. If there is a lower bound on DC bar, then we can also then we can find lower bounds of a very specific type. And so this is what I want to talk about. So say Vm is now the vector space of polynomials in m squared variables of degree m. Right? This is where the permanent lives in our Vm. Right? This is our space. It has a dimension that is quite large, right? It's m squared plus m minus 1 choose m. Right? The basis of this vector space is given by the monomials. Right? And now this is just a finite dimensional vector space. It's a complex numbers. It's the ground field. This is just a finite dimensional vector space, so we have a usual metric, right? So if you have two polynomials, in particular, you can just measure distances of polynomials, right? But just a polynomial is just the vector of its coefficients, and you can have two polynomials as two vectors of coefficients. Just measure the distance of these two in the usual way. So gives you, I mean, having this metric on the space gives you a very natural way of, the natural way of defining what is a continuous function from the vector space to C. So for each polynomial, so if you have such a function f, so bear with me a bit because f was all kinds of things today, but f is now always precisely this. It's a function that on your vector space that maps to C. It will be always such a function. So in particular, you can evaluate it at every point, at every polynomial, and you can assign to every polynomial a complex number, right? You can. This is what it does. And now, if you want to prove a lower bound, what you actually want to have is a function that is that vanishes on all things that have a low complexity, but it doesn't vanish on your point, right? Because then you prove that your point has a high complexity. That in itself is not a big observation. But now the thing is, if we study DC bar, we can say a lot of things actually about our functions f. So the first thing comes from elementary point set topology. That is not very deep, but it says if actually there is any lower bound on this DC bar here, say we have a fixed m, fixed n, all the time there will be no asymptotics here. There will always be a fixed little m and a fixed bigger n. Also, so m and n is different than in Greta Panova's talk, so it is switched. At some point in 2011, there was a switch between m and n. So in the papers, I mean, different authors then use different, Anyway, you can, so just to make you aware of that. So we can actually say that this function here, there exists a continuous function f that gives us the separation. So it is 0 on all the functions, on all polynomials here that have a low DC bar, but it's non-zero on the permanent. So and what is this function? So we can be actually more specific. The function, take the set of all the low complexity polynomials, and now your function is just the distance function to that set, right? So this is precisely the function, and this gives you the separation. And this only works because we're looking at DC bar. If you're looking at DC, then this is not true anymore, because the distance function would not have this, distance function would not work. And a distance function would be continuous, but it wouldn't work like this. in particular, it wouldn't be non-zero, right? It could be 0 at some point there. Okay, so that is you get so this means that you don't. That's already pretty nice. We only have to look if we want to prove lower bounds. We only have to look at continuous functions. So, but now we go much further. So we have algebraic geometry gives us something even stronger. If we have a lower bound, then there exists a polynomial function even that has the same properties. So it vanishes on all the low complexity polynomials, and for the permanent it is non-zero. And if we want to have representation theory, want to bring this into the picture, then this gives us even stronger properties of the functions that we only have to look at. And there will be not so many functions actually that could possibly give a lower bound. So we will have a rich mathematical structure that will tell us where to look actually. So what's a polynomial function here on such a vector space? Let me give you actually quite a nice example. This is very classical. So consider a quadratic homogeneous polynomial. This is our point h. Ax squared plus bxy plus cy squared, right? So, and the a, b, and c, those are complex numbers. And now we look at, can we write this polynomial as a square of a linear form? So in this form, h should be alpha x plus beta y squared, and those should be complex numbers. This is our question, and we can do this exactly if its discriminant vanishes. And the discriminant is b squared minus 4ac, so you might have seen that, right, in high school. So in particular, yeah, this case, if you dehomogenize this case, so setting y equals 1, you get exactly the high school case. That's ax squared plus bx plus c has a double root if and only if b squared minus 4ac is 0. So what is this b squared minus 4ac? This is precisely what we think of as a polynomial on this space of polynomials, right? Because this is now a polynomial, and the variables are the coefficient of other polynomials, right? So now here, I mean, again, this polynomial h is only interpreted as its coefficient vector. There's only this a, b, and c, and this is a vector in c cube. And we have a polynomial is b squared minus 4ac. This already here gives us a nice little toy complexity lower bound, right? So if now our discriminant does not vanish on a polynomial, this says that we need at least 2 summons to write our h, right? So it's a lower bound on its complexity. The complexity is precisely the symmetric rank or the Warring rank that we just discussed in the last talk. So this is precise, and so this is a toy case for precisely these kinds of functions that we want to look at. It will be precisely these kind of functions. Okay? So those are polynomials on vector spaces looking like the discriminant. And yeah, so let's just recall, we find these polynomial functions, but now we can do even more. So better, we can restrict ourselves actually not only to polynomials, these will always be homogeneous polynomials. This is also very easy to see from algebraic geometry. If you have a polynomial that's not homogeneous, you can take one of the homogeneous parts, it will always give you the correct answer, right? And now representation theory can make a much stronger statement. And I try to tell you what it does. It will be tiny bit more complicated though. Okay, so recall this is our space. It's the space of VM. Yeah, so this is a bit hard to read, but I mean it's just the homogeneous degree m polynomials in m squared variables. And now we want to look at possible functions that could give us separations. This should be the degree d polynomials now on this space, right? I mean, like the discriminant was a degree 2 polynomial. So so this should be the space of homogeneous degree d polynomials, and now the variables are degree m monomials in these m squared variables, right? This should be the natural setup. It's the generalization of the discriminant, right? So you have some polynomial on this vector space of polynomials. This dimension here is very high. So this is the formula. It has a binomial coefficient inside some binomial coefficient, right? Because you have binomial coefficient twice now, right? So these spaces can actually now be studied with representation theory, despite their very high dimension. So the example here is now for the discriminant. Let's just do for the discriminant. So V should be our space of polynomials. It's just basis is x squared, xy, and y squared. Dimension is 3, and the dimension now of our new vector space here that we want to look at, where our possible separating polynomials live, that is 6, and it has a basis a squared, ab, ac, b squared, bc, and c squared. Right? It's a 6-dimensional vector space. This is where our possible separation polynomials could live. Yeah, so, all right. So now, what can representation theory tell us now about this 6-dimensional space? I mean, this also works, of course, in much higher dimensions. Right? So this decomposes uniquely into a sum of what is called isotypic components, and they are indexed, so just give it a symbol W, and they are indexed by some lambda, and we only have to search for f inside these isotypic components. So what you get is a direct sum into so-called isotypic components. The sum, these lambdas are nothing complicated. The lambdas are the easiest thing of all. Those are just partitions of d times m into at most m squared parts. And I give you an example here. Say d is 5, m is 2. Then, for example, 5, 3, 1, 1 is a partition of 10 into 4 parts, right? So it's just the numbers add up to 10, and it is ordered. It's sorted, right?
What does isotypic mean?
Yes, isotypic. I will come to this. So I will come to this in a second. Right? Isotypic will, yeah. I will define what the isotypic components are.
No, what is isotypic, the word?
Oh, the word means that all the irreducibles in the component are isomorphic. They are all of the same type. They are isotypic. If you decompose this into irreducibles, then you group the irreducibles of the same type, and this gives you the isotypic component.
Okay, so you're taking the space and you're reducing it into its irreducible modules, and then you're grouping these modules some way.
Yes, and grouping them by just taking their sum as a vector spaces.
No, but like, okay, but you have this decomposition irreducibles, and then
This is canonical, the other one is not. So into irreducibles is not canonical. So you can do this in several ways. If you have more than one that have the same type, then this decomposition is not unique. So you just regard them as a single vector space.
so it would be unique if all the multiplicities were 1. But
Yes.
if you have higher multiplicities, then it's just like that space.
Yes, yes. You have to group them. Otherwise, you can shift them around, and yes. So you group them together, and you call them an isotypic component. Yes. I mean, yeah. So for the others who did not just follow this discussion, it will be fine. So this decomposes into just, and you will see examples how this decomposes. So, but now I'm saying, if we have such a decomposition, that's really nice, because in each of these components, we only have to look at so-called highest weight vectors. And I will also tell you what those are. If we want to prove lower bounds, it's the same statement. It's precisely that we can restrict ourselves to highest weight vectors, and those live in isotypic components. And that's all we have to look at. Let me give you an example here. So this is there should be a 2 here. Again, I mean, it should be the old example, right? It should be the discriminant. So b squared minus 4ac will actually be a highest weight vector, and it will live in an isotypic component. And then this isotypic component is one-dimensional, and here the lambda will just be some easy partition 2, 2. And then there will be a second highest weight vector, which is a squared. This is another highest vector, but this one lives now in a 5-dimensional isotypic component and has a different type. It's 4, 0, right? So those will be the types. So these lambdas are not scary. They are just partitions, right? Okay, so let me tell you what these things are. So for this, I want to talk a tiny bit about group actions, because now, this is what makes the whole thing going, is that you can look at your separating polynomials, and you can actually move them around by group actions. So this is what will happen. So let's just take our example b squared minus 4ac, right? Just to recall. And we want to permute now this x and y. Underlying these b squared minus 4ac, let's just interchange all the x's with all the y's indicated by this permutation matrix here. And what happens is that the b stays itself, because if you switch an x into y in the b, it just stays b, right? But the a becomes a c, and the c becomes an a. So if you act with this matrix on the f, you get a b squared minus 4ca, which is still f, right? So this operation does not change f, right? So f is fixed under this operation. Let's do some other operations, right? Let's do some scaling operation. Let's scale x by some constant gamma and y by some constant delta. So indicated by this matrix here, what happens is that the b gets scaled by a gamma delta, right? And the a gets scaled by a gamma square, because it's x squared, and the c gets squared by multiplied by a delta square. Right, so in total, if you do the calculation, this is gamma squared delta squared f. So this means that this polynomial gets actually just scaled by gamma squared, delta squared, if you act on it with diagonal matrices. That will be a key property. You want to always know how your polynomials act, if you or how your polynomials get stretched if you act on them by some diagonal matrix, which is sometimes called the algebraic torus. So, but you don't have to call it like that. It's just diagonal matrices, right? So, and now you look at the vector of the scaling exponent. So you have a 2 here, gamma squared, delta squared gives you a 2, 2. And this is precisely, this will give you the type, right? So you remember the b squared minus 4ac had a type 2, 2. It's precisely this 2, 2 here that you see here. So the type lambda is not a complicated thing. It's just how it reacts to the action of a diagonal matrix. And the scaling, if you look at the scaling exponent of a squared, it's precisely 4, 0, right? We saw, also we saw that the type of the isotypic component is 4, 0, which is precisely the type, is the scaling exponent. And one more example is upper triangular matrices. If you act on them, on this a squared, say this is an upper triangular matrix, so it sends x to x and sends y to alpha x plus y, so it doesn't change a squared, right? Because the a is just an x squared, x is sent to x, so an upper triangular matrix just also fixes fixes a squared in this case, right? So those is fixed. So this is just to take away all the, basically saying that this is not very complicated, and you can define how general matrices actually act on these polynomials in a very, very natural way, right? This is complete. This is just the normal generalization. There's only one way of doing this now, so that all these examples work like this, right? I mean, therefore, I think it's now clear how you could actually act with matrices on these separating polynomials, right? Okay, or are there any questions about this? Okay, so now what is the highest weight vector? So a highest weight vector is a vector that does not change under the action of any upper triangular matrices, so we saw that, and gets scaled under the action of diagonal matrices, and now it has a type. So the vector of scaling exponents is called the type, okay? So and if you want to know what an isotypic component is, I didn't put it on the board, but the isotypic component is you take all the highest weight vectors of the same type, and you act with all the group elements that you have in your group, and you take their linear span, and that's the isotypic component. So and then there's a theorem that this the isotypic decomposition is the unique decomposition that there are no overlaps and everything is fine, right? But that's of course a representation theory. Yeah, we don't have to go into the proof of these things now, right? So in the example we have our two highest weight vectors, b squared minus 4ac of a type 2, 2 and a squared of a type 4, 0. And yeah, they form a vector space, right? If you have two highest weight vectors, they form a vector of the same type. You can add them or scale them, do any linear combinations of them, and they are still highest weight vectors of the same type, right? Because they don't change under upper triangular matrices. Then, since these actions are all linear, so that you immediately see that this will give you a vector space. And yeah, sometimes I call this the highest weight vector space of a certain type, right? And it will be very important because in this vector space you have to search for the separating polynomials. These are the only vector spaces you have to search for separating polynomials. You don't have to search in any other vector spaces. And so those highest weight vector spaces, they lie in isotypic component. And now lower bounds are always given by highest weight vectors. Basically says if there is a lower bound on DC bar of the permanent. I mean, this is also independent of the permanent, of course, right? I mean, it works for every polynomial. It's very general. Also, it doesn't only work for DC bar. It works in a very high generality, right? But okay, so if there is a lower bound, then there is a highest weight vector f of some type lambda, and this highest weight vector vanishes on all the polynomials with a low complexity, but it doesn't vanish on the permanent. So this is not quite true, but you have to well, this is a tiny technicality. You can just ignore that actually. So basically it says that you only have to look at highest weight vectors for separation, right? And so these are not scary, these vectors. I mean, the examples are not scary, but there are actually concrete algorithms for constructing highest weight vectors, and they're using multilinear algebra. So there are actually ways of constructing them. I mean, there are many questions about these things, in particular about the dimensions of these spaces. But if you really want to construct them, there are methods to doing so. You don't have to put these conditions into MATLAB and see what's coming out of this. I mean, there are much better ways of constructing these vectors, and there's a well-developed theory about these vectors.
Wait, so then
Sorry.
So then just looking for highest weight vector is not enough if I
But the G's, yeah, I mean, yes, but the G is, you can take, for example, a random G works.
Oh, random G works.
Yeah, random G always works, yes. A random G always works, so that if you take a random.
Also, the concrete algorithm is just use some variety, and then you have, apart from some closed condition.
Yes, it's apart from some closed condition, yes. Yes, yes, yes. It's basically saying, so this works if you take a generic torus, but if, as I define it with this, where I defined the specific diagonal matrices, so this will give you a base change to a generic torus, right, to a different torus, and then everything works nicely. So just take a random matrix, it works. But I mean, you can also, so I have a, for example, I proved a lower bound where I explicitly gave it G, so this also works. It doesn't seem so very difficult to get. Yes, random ones work. Yes.
The polynomial d square minus 4ac is invariant under SL2.
Yes, indeed it is. Yes.
So do you have examples of separating polynomials which are not invariant under SLM?
Yes. Yes, we have. For example, the border rank of 2 times 2 matrix multiplication is 7, and this can be shown by a degree 19 highest weight vector. That is not an invariant. Yes. So, for example, but I mean,
Can you show that there are no invariants in this case? Or
you can also do it with invariants.
with invariants?
Yes, but the question was, can you do it without invariants?
Yeah.
Yes, you can also do it without invariants. Normally, it's easier to do it without invariants.
So this is saying that we could, instead of SLM, we could replace it by upper triangular matrices.
You could, in principle, always try to separate if you are careful, and you have to and some subtleties. You take care of some subtleties. Then you can actually make it so that you can always do this with invariants. Yes, that is true. But the degree of the invariance is conjectured to be very, very high. But in principle, that is possible if you are careful. So if you get rid of padded polynomials and things like that, if you look at the homogeneous iterated matrix multiplication, then it's a setup. You can make a setup where you can do basically GCT, where you can separate with invariants. Yes.
So the separating with invariants is hard because you're going to say now that all the invariant polynomials they have a huge stabilizer, right? So then like it's much. They have a lot of constraints.
It is the main problem with the invariants is that their degree is very, very, very high. That is the main problem. But I mean, a priori there is no problem with invariants. So also I found separations with invariants also. So I mean, it's not. Sometimes they just appear, and then so computer calculations certainly have a problem if you want to do this with invariants. If you want to do computer calculations, then those would be have a too high degree. But I mean, there could be theoretical results that give you actually I don't see any problems with that actually. If you want to do that.
Well, the degree would be very high.
Yes, but I don't see any theoretical problem with trying to separate with invariants. So a priori, I mean, degree would be very, very high. So the example is known where the degree is astronomically high of the invariants. But if you have,
You have to show it.
Hmm?
You have to show that it separates. That
yes, I understand that. I understand that. But I mean, you might be a genius and then find out there's this invariant with this and this properties. I don't know. I mean, it seems to be much easier to just use the highest weight vectors.
You're saying invariant, are they high degree in an asymptotic sense or in a practical sense? Or both?
I think both. I think it's both. So invariants, for the people who were not following this, invariants are the ones where all the numbers are the same. So the 2 is an invariant. You can always restrict yourself to that case, but yeah. So people I talked with, they think might be for several. Well, I mean, for the growth of the degree was the problem that they mentioned most often for separating with invariants. All right, but in principle you could. Okay, so how can we? Yeah, so now let me go to the result of the paper that I want to present. So how could we possibly find obstructions? So yeah, okay. Okay, we put an n here if it's the points, if it's the polynomials that have a low complexity. Okay, so this if the Vm of n is just the low complexity points. And now to simplify the study of these highest weight vectors, so Multiplicities and Zerhoni did not want to look at these highest weight vectors, which is understandable. So they introduced the following approach, and it's an occurrence obstruction approach. Those are null chord occurrence obstructions. So, and it's the following proposition, which is true. So for a partition lambda, if all highest weight vectors of a type lambda, they vanish on the low complexity polynomials, and one of them just satisfies it doesn't vanish on the permanent, then we got a lower bound, certainly, right? So on the rationale for this is the vanishing of all highest weight vectors could be easier to study than analyzing specific highest weight vectors. So in particular, the approach does not even touch highest weight vectors, but only looks at the type. And then you can say a lot about what all highest weight vectors do. You don't have to look at because the highest weight vectors, they get also quite complicated at some point. And they even gave a sufficient criterion for the vanishing of all highest weight vectors. And the criterion is a vanishing of the rectangular Kronecker coefficient. So if a rectangular Kronecker coefficient, and I denote this by g of lambda dm, if this number is a natural number, could be 0. But so if it is 0, then all highest weight vectors of this type lambda, they vanish on the low complexity polynomials. So now this is I mean, knowing this gives us hope that one might actually find this to be true in a lot of situations, so that you can actually prove good lower bounds. So how is this defined? So for the people who know representation theory, this coefficient now has a nice definition actually in the representation theory of the symmetric group. It's a classically studied object. It's the multiplicity of the irreducible spectrum module lambda in the tensor product dm, tensor dm. But if you don't know that, that's also fine. So it does not have I'll give you some properties, I guess, on the next slides of this thing. Yeah, so studied since the 1950s. There are many papers that treat special cases of these coefficients, but it's actually a mostly not understood coefficients. It's actually active area of research, and people are meeting every few years, having large conferences, and semi-large conferences about this coefficient. There are actually conferences that are study precisely these coefficients, right? I mean, this is the only topic. It's only these coefficients. And so we actually contributed quite a lot with Momulai and Walter. We have a paper that says deciding the positivity of these coefficients is NP hard. So that was not known before. And so what we did is in a certain subcase, we can actually interpret this coefficient now as some combinatorial quantity. So we knew in that case what to count, and we could show NP hardness of that thing. And that was actually, that's a bit cheating because it was actually done for us. So there was a paper that basically said precisely what you just identified as the Kronecker coefficient is actually NP hard to decide positivity for. So that was actually really nice. The literature gave us basically NP hardness here. Okay, so open question. This is still an open question. This is this function that calculates the Kronecker coefficients. Say you got a lambda and a d and an n. Is this actually in sharp p? It's not known. It's a function that always spits out natural numbers, but it's not known if this is actually a sharp p function. So it is in gap p. So there are exponentially sized formulas that give you in the end. So they have subtractions is the problem. I mean, it's a sharp p function minus another sharp p function. And so this is also, so combinatoricists find this very important to find out if this problem is in sharp p. For the general Kronecker coefficient, the containment in sharp p is listed as problem 10 in Stanley's list. So from the year 2000 of the outstanding open problems in algebraic combinatorics related to positivity. So these people really want to know. So they don't formulate it in this way. They formulate it in the way we want to have a combinatorial description of the coefficient, but it's basically this. It's basically exactly asking, is this function in sharp p? Right? Is this function in sharp p? All right. So they were looking at all this, looking at all this work that's been done, all this work that's going on, and all these questions that mathematicians are asking. It was reasonable now to try to use this in geometric complexity theory because it's something deep. It's something nice, and it looked non-trivial enough so that it could actually give us something really nice, but it doesn't, right? So the result is that with Greta Panova is that it does not give us lower bounds better than quartic. This is the result. So the vanishing of these coefficients, of these rectangular Kronecker coefficients, cannot be used to prove superquartic lower bounds. And the proof idea of this is you show that in all the relevant cases, you either have that this coefficient is positive, Or it might happen that it's not. So actually it might happen that it is not positive, and that also led to these conjectures, right? It's actually quite often that it is not positive. It's often very often actually 0. But in these cases, we can show that there's actually no highest weight vector of type lambda. So I mean, so and then then you know that the coefficient is 0. You would just take a highest weight vector now and use it as a separating function, but there is just no such highest weight vector. So in all these cases, we can always show that there's just no highest weight vector. And yeah, so for the people who, yeah, let me just give you some ingredients of the proof. So you might have, so just to know what kind of whose results are actually involved. So main ingredients are, there's a result by Kadish and Dunsberg from 2012 about paired polynomials, gives significant restrictions to the possible lambdas that could be used for proving lower bounds. I didn't put this on the slide, but it basically says that if you, and it holds also, I mean, it's actually reasonable to think of this independently. It's another restriction, so the lambdas will always have a very long first row. So when you prove a lower bound, when you want your lambda to prove a lower bound, the first number is, the largest number in your partition will be very, very large in comparison to the rest of the numbers. So that they proved. And we used some properties of the Kronecker coefficient, stability properties proved by Manivelle in 2011 to enable us to prove a lower bound on a possible degree d. So degree d was the degree of your separating function, and you prove a lower bound on that degree. So you show that no small degree function can actually give you separations. And the proof of that one is quite interesting. It works as follows. So you assume there is obstruction, and by obstruction I mean a separating function in a low degree. Then you can show that that this DC bar of the permanent is not finite anymore. So you can use that low degree separating function to make better and better and better obstructions. But you can do this infinitely often, because this coefficient stabilizes at some point and gives you better and better and better and better bounds infinitely often, right? So this is not possible. So this gave us a degree lower bound. We used also a representation theoretical result by Bessenroth and Behns. Behns is a student of Bessenroth, and Bessenroth is a researcher who has a lot of papers about Kronecker coefficients. This was one of them. They're using character theory to prove some positivity results about Kronecker coefficients, and the semigroup property is has an own backstory. Let me just not go into that. Okay, so those were ingredients. Yeah, so open questions is, so indeed this approach now doesn't work with the vanishing of Kronecker coefficients, right? And it's a bit worse actually, so it's not only that it doesn't work for Kronecker coefficients, but I want to say actually that this paper contains many partial results that work for other multiplicities as well. So if you don't look at these only these Kronecker coefficients, but look at the m lambdas that were in Greta Panova's talk, if you only look at vanishing or non-vanishing of the m lambdas, then a lot of properties carry over to these m lambdas. So in particular, you get a degree lower bound as well, and you get a lot of positivity results, and we are currently working on just basically lifting this to the m lambdas. So I don't think there's much more to be done for that paper, so it should be done actually quite soon. So this means that this vanishing of the multiplicities, I would say, does not have much hope to give you any good lower bounds. But I mean, just let me rephrase maybe, because maybe this sounds now too negative. I mean, we know, let me say this again, we know that if there is a lower bound, right? So if this grows superpolynomially, then there are highest weight vectors that prove that. And they have a type lambda, and you can write them down. They do exactly what you think. So so these are precisely the things that give you lower bounds, right? And it's even in the best lower bound by Landsberg, Manivelle, and Resser, they specify precisely not only the lambda, but the highest weight vector, right? So they actually write down, this is lambda, this is the type, right? They actually have this in their paper. Yeah, so open question is that should be answered if one wants to understand better what these highest weight vectors are. So say we have an m and a d and a lambda, right? So some degree of our separating polynomial, some type lambda. What's the dimension of this vector space of highest weight vectors? I already said that this is sometimes a bit complicated. So how many vectors of this type are there? And this dimension has a name. It's called the plethism coefficient. it's some other. I mean, it's some other coefficient, but I mean, you know basically its definition now, right? It's the dimension of this highest weight vector space, and this is also a coefficient that combinatorists care about a lot. This even is problem number 9 now in Stanley's list from 2000. So precisely the things that are actually that GCT cares about, right? I mean, those are exactly problems in Stanley's list, right? So combinatorists care about this also a lot. Okay, so yeah, so what one could do is now, well, so vanishing does not work. So one can have the idea, I mean, if one really does not want to touch the highest weight vectors, there's still the hope that one could say something more, but not just looking at vanishing, right? We want to maybe look at the so-called multiplicities, and those are the dimensions of the highest weight vector spaces. So a rationale for this is the determinant polynomial and the permanent polynomial characterized by their symmetries. So now one could have a look at the dimensions of the highest weight vector spaces. So it could be sufficient that these dimensions just give you just are enough to prove superpolynomial lower bounds. If the dimensions are if one dimension is bigger than the other, then you actually get a lower bound. You can so this can be shown. It's not necessary that the Kronecker coefficient is 0. It's just necessary that some dimension of a highest weight vector space is less than some other dimension of a highest weight vector space. That's enough to actually show a lower bound. But so what the problem is, I mean, there is actually no problem with that at the moment. It's just that this hasn't been looked at much. So the results that study this possibility are rare. So there's a paper by Larsen and Pink from 1990 that studies orbits, and for orbits this works. For orbits, this actually also works with occurrence. So I'm not so sure how much we can draw from this paper, but sometimes this actually works, given some bounds. For example, for the border rank of matrix multiplication, all this setup can be applied, and you get a lower bound of 3/2m squared for the m by m matrix multiplication tensor. That is, yeah, it's at that point it's unclear how to draw much from that as well. So this is actually these multiplicities are not very well understood. So so the question, okay,
Can you just talk
yes.
again about what are I just got lost.
Multiplicities are the dimensions of the highest weight vector spaces. So and you look at yes. So one of them was the plethysm coefficient, but now we want to look at other ones. We want to look at dimensions of highest vector spaces in it will be dimension in highest vector spaces in vanishing ideals. You want to know how many vanish on low. You want to know the vector space of highest weight vectors that vanish on low complexity polynomials. That's, for example, one of its dimension is a multiplicity. It's always less or equal to the plethysm coefficient, where some vanish on low complexity polynomials and some don't. So complexity at most n polynomials and some don't. And you get some multiplicity, some integer that is less or equal to the plethysm coefficient. And you want to study that. And you want to know how large is that.
So this is not the same as just collecting all irreducible representations of a certain shape? This is precisely collecting them. This is a plethysm coefficient. It's precisely collecting them. And now you want to know how many vanish on complexity at most n polynomials. How many vanish? And for that, actually, it depends on how you group your irreducibles. So you're better looking at the isotypic component and looking at how large is the subspace that's vanishing, right? So you're looking at you take the vanishing ideal and then you decompose it into irreducibles. That's what you could do, and that's what you want to look at. And those are the multiplicities, and yeah. So, and the question is now: can such a consideration where you only care about dimensions of highest weight vectors, dimension of highest weight vector spaces, can this actually settle questions, right? Can this actually be used to settle questions? I don't know. So can we settle this question are these dimensions enough? Can we settle this question in a similar but simpler setting than determinant versus permanent? For example, one could look at tensor rank, or one could look at symmetric rank, or anything that you want that is
close enough to the original question, because the determinant versus permanent question, I mean, you have, for example, the points are characterized by their stabilizer. If this is not the case, if your points are not characterized by the stabilizer, so in general, this is known to not work. So one can construct artificial settings where this does not work, but those settings are very different in nature from the determinant versus permanent, right? In particular, the points are not defined by their symmetry. So what one does is one cooks up some very artificial setting and then sees it doesn't work. But it doesn't give any information about our problem at hand. We need to know what are the key properties in this determinant versus permanent setting, and one of the key properties could be that these points are determined by their stabilizer, by their symmetries, right? That could be one of the key properties that maybe makes it possible to separate by just looking at these multiplicities. And so this might or might not work, and one should definitely have a look at easier example and see. I mean, at least in one smaller case, is this possible or not, to give some intuition at least if this is a valid approach or not. So it might well be a very valid approach that avoids touching the single highest weight vectors. Right? You don't actually have to write down a discriminant like very, very large polynomials, because these polynomials also get very, very large if you write them down. Right? You want to avoid touching them and then only look at these kind of multiplicities. Okay, and that's it. Yes, yes.
So there is a small bound between what we currently have a lower bound for the border determinantal complexity and what you've shown that we can prove with the highest weight vectors.
Yes.
So do you have any intuition? Do you believe that is it worth pursuing an improvement on the lower bound just by polynomial factor using this technique?
So I used this technique for the. I'm not saying it's a technique. I'm basically just saying these exist. So the question is if you should start searching for them in the first place. And this is the question, right? That would be a technique, right? Technique would just say, I know that there must be highest weight vectors. I want to look for them specifically now, instead of doing some other flattening techniques or things like that, right? And I don't know. I don't know if that is I do know that I proved lower bounds with those. I mean, with this, by just going for the highest weight vectors. So the 3/2 m squared for the border rank of matrix multiplication, for example, comes from explicit construction of a highest weight vector from nothing. I mean, and it's even, those equations that you get are even interesting for geometers, because the equations that you get when you're going for the highest weight vectors directly, those are not clear that those should come from any flattening technique. So normally the lower bounds that people look at, so if you do any tensor flattening, Young flattenings, or partial derivatives, shifted partial derivatives, those all come from flattening tensors, right? You basically transform everything to some large matrix and take the rank, basically, right? So basically your separating equations are always subdeterminants, right, of this large matrix. Those are your separating polynomials. And these polynomials that you get here, there are some very different polynomials among them, right? So they don't always come from these kinds of constructions. So they actually look different, but they also look not so easy to understand. So I'm not saying that this will be the fastest approach towards the problem, but certainly, first of all, it says those always exist. And second, it says that the other constructions, they fail actually to find them. If you take the usual constructions by flattening a linear algebra, they sometimes fail to find these. So that's the only thing I can say about it.
Could you expect to improve the m squared by 2 lower bound using this to m to the 4? Because you said you cannot expect beyond m to the 4.
So of course, before proving the negative result, I try to prove some positive results, right? I did not have any success with that. I did find some interesting things. So so this is not the vanishing Kronecker coefficient actually happens, and you can use it to prove lower bounds in very small cases. So it actually works. So you can for example, prove that a homogeneous degree 3 polynomial in 7 variables, if you take a generic 1, is not in the orbit closure of the 3 by 3 determinant. That's a very, very small, tiny statement, but it's proven by vanishing of a Kronecker coefficient. So you can actually do that. You give it a precise lambda, the Kronecker coefficient is 0. You find the highest weight vector by proving the plethysm coefficient is positive, and it gives you precisely that bound. So that actually works. It's just computer calculations stop at some point. These get quite intense, and then you can only do small examples. So for the tensor rank, it's actually nicer. If you look at tensor rank, then these techniques go a bit further because the computer calculations are not as involved here. The number of variables grows quicker here, and things in general are a bit slower on the computer. So you cannot go to this high degrees here in the determinant versus permanent setting. Therefore, the 3 by 3 determinant is basically what you can do, and then 4 by 4 is already, you cannot, the plethysm coefficient is just out of reach for that. Even that's out of reach.
So one more question.
Yes?
So if I look at rectangular coefficients, the reason why it's interesting in rectangular coefficients is because the stabilizer of the determinant tells you that you need those things.
Yes, exactly those.
But that is just the orbit.
Sorry?
That is only the orbit. It is not
Exactly, this is only the orbit, yes. So
not the orbit closure.
no, this is not the orbit closure. So this result that I just presented is using the coefficients on the orbit only. We are working on the result for the orbit closure, and I expect the same result to hold in the orbit closure. It's maybe not quartic, maybe it's some higher exponent that doesn't work, but it will be some result like that. I don't see any way of I don't see any way how this could work, because so many results actually of this paper carry over to the closure. It's only some, at the very end there are specific Kronecker calculations, and those need to be lifted now, and we are on our way of doing this at the moment. So I don't expect this to be a very different situation. But this is only telling about vanishing, right? It's only vanishing, right? So basically the occurrence of a type should be not enough. Maybe it's probably not enough to separate. This is unfortunate.
Maybe you have more questions? No. So in a way, again, ties up with what Ethan was saying in the morning, that you need to look at the boundary. You need to really know what the boundary is. At least that's what from your results you can say. If I just look at the orbit, I don't see that.
No, the orbit. The Kronecker coefficients tell you something about the orbit, but you can. You actually have to look at multiplicities, I think.
You have to look at both the border and the values. Just the values.
The values might, yes, you might have to look at the values.
Everything is going to get harder.
It gets very hard.
So it's just the short. So this was a shortcut that was proposed, but the long cut is the one.
Yeah. So the problem with the long cut is that we don't have many good ways of actually getting our hands on these multiplicities at the moment, right? Even plethysm coefficient is.
Psychologically prepare ourselves for the.
Yeah, it will not be done in the next few years with this method, I guess. But I'm not saying it's not working, right? Okay.